Find a wall, stand facing it, close enough to touch, and put one foot forward so the tip of your big toe sits roughly a hand's width back from the skirting board. Point the foot straight at the wall, not turned out, not angled in, straight. Now press that heel flat into the floor and hold it there. Drive your knee forward until it touches the wall. If the knee touches easily and the heel never lifts, slide the foot back a centimeter and go again. Keep sliding back until you find the furthest point where the knee still reaches the wall and the heel still holds the floor. That is your number. Measure from the tip of the big toe to the wall. Write it down. Now do the other leg and write that one down too. Physiotherapists have been running this measurement for decades under the name the weight-bearing lunge test, and Bennell and colleagues published its reliability data in the Australian Journal of Physiotherapy in 1998, establishing that the same clinician measuring the same ankle on different days lands within a few millimeters. It costs nothing. It takes 90 seconds. It requires a wall and a ruler. Most healthy adults reach somewhere between 10 and 12 centimeters. Below 9, something has closed. Below 6, it has been closing for a long time. Then look at the gap between your two numbers. If one leg gives you 11 and the other gives you 7, that 4 centimeter difference is carrying more information than either figure on its own, and I will come back to exactly why near the end. Here is the part that makes this test strange. You just drove your knee at a wall, and your knee is not what got measured. The measurement was taken at the ankle. The joint it makes a prediction about is the knee, sitting 15 centimeters above the thing that was actually tested, currently silent, currently fine, currently giving you no reason at all to think about it. Almost every test in orthopedics works the other way round. Something hurts, so you go looking at the thing that hurts. An X-ray of a painful knee finds the joint space narrowed. An MRI finds the cartilage thinned, the meniscus frayed, the bone underneath reacting. All of it accurate. All of it late. By the time an imaging study can see the damage has been accumulating for somewhere between 5 and 20 years, and every one of those years was mechanically caused by something that was already measurable and never measured. The wall test does not look for damage. It looks for the mechanical condition that produces the damage, and that condition arrives first. There is a reason this particular ankle measurement carries so much freight, and it comes down to a single fact about how the human leg moves that almost nobody is taught. When you walk, when you go down a step, when you lower yourself into a chair, your foot is planted, and your shin has to travel forward over it. Not the other way round. The foot stays. The shin swings. The distance that shin can travel is fixed by the ankle, and when the ankle runs out of travel, the leg does not stop moving. It finds the movement somewhere else. That is the whole video. Everything from here is the mechanism, the evidence, and what you do about the number you just wrote down. Start with the shin. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. Stand up and take one step forward, slowly, and watch the front leg. Your heel makes contact. Your foot rolls down flat, and then, for about 0.6 of a second, that foot sits welded to the ground while your entire body passes over the top of it. Your shin rotates forward at the ankle, hinging on the dome of the talus, carrying your knee and your hip and your torso ahead of the planted foot until your weight has moved far enough forward that the heel can lift and the toes can push off. That forward rotation of the shin over the foot is called dorsiflexion, and it is the single most heavily used motion in the human leg. It happens roughly 10,000 times a day. Nobody thinks about it once. Level walking on a flat floor demands about 10 degrees of it. Rising out of a chair without using your hands demands closer to 15 or 20, because your shin has to come much further forward before your center of mass sits over your feet. A full squat, heels down, thighs below parallel, demands somewhere in the region of 35 to 40. Then there is the one that breaks people. Going downstairs demands more dorsiflexion than going up them, and it demands it while one leg holds your whole body weight and lowers it under control. On the way up, you push. Your quadriceps shortens as it contracts, which is the easy direction. On the way down, you lower. Your quadriceps has to lengthen while it contracts, resisting gravity the whole way, and at the same instant your standing shin has to travel forward over a foot that is stuck on a narrow tread, while your other foot reaches into empty air for the step below. The load on the kneecap during this is not a small number. Riley and Martins measured patellofemoral joint reaction force back in 1972, and their figures have held up. Level walking loads the joint behind your kneecap at roughly half your body weight. Climbing stairs pushes it past 3 times body weight. Descending is higher again. A deep squat can drive it to more than 7 times body weight. Run that for someone weighing 75 kilograms. Every stair they come down is pushing something in the region of 250 kilograms of compressive force through the back of the kneecap, and the surface absorbing it is not large. The contact patch between the patella and the groove it slides in is a few square centimeters, and it shifts position as the knee bends, precisely so the load never sits in one place too long. The cartilage on the back of the kneecap is the thickest articular cartilage anywhere in the human body, 5 to 7 millimeters in places. That thickness is not decorative. It is there because the forces are enormous and the surface area is small, and evolution has been solving that arithmetic for a very long time. None of this is a problem when the joint is loaded the way it was built to be loaded. Cartilage under compression does fine. It has no blood supply, so it feeds itself by being squeezed. Load compresses it, fluid moves out. Load releases, fluid moves back in carrying nutrients with it. A knee that gets used gets fed. Stillness starves it. The problem is never the size of the load. The problem is where on the surface the load lands, and whether it lands there every single time. And where it lands is decided almost entirely by whether the shin below it can travel far enough forward. Hold on to the repetition figure for a moment, because it is doing more work than the force figure. A person taking 7,000 steps a day loads that joint 7,000 times. Add 2 flights of stairs, up and down, and you have added another 80 repetitions at 6 times the pressure. Over a year that is 2.5 million loading cycles. Over 30 years it is 75 million. A mechanical fault that shifts the contact point by 2 or 3 millimeters is nothing on any single repetition. Nobody could feel it. Multiply it by 75 million and it stops being nothing. My grandmother could not have told you a single one of those numbers. She could tell you from across a room who was about to have a bad winter. She watched how people came down the stairs. She noticed when someone started taking them one at a time instead of alternating, when the hand went to the rail before the first step rather than after, when the whole body turned sideways to come down. She never called it anything. She just said that so-and-so had got careful on the stairs, and she said it the way you would report a diagnosis. She was reading the highest demand dorsiflexion task in ordinary life and watching people quietly stop doing it properly. The gait lab took another 40 years to explain what she was looking at. Your nervous system has one non-negotiable instruction during the stance phase. Get the body over the foot. Whatever it takes. It will not stop mid-step because the ankle is 4 degrees short. It will not refuse to descend the stair. It completes the task, every time. And if the range it needs is missing at the ankle, it takes that range from whatever joint will give it up. The leg has 3 places to borrow from, and it uses all of them. The first is the foot itself. Below the true ankle joint sits the subtalar joint, and below that the midfoot, and both of them can move. When the shin cannot hinge far enough forward at the ankle, the foot rolls inward and the arch drops. The heel tips outward, the navicular sinks, and the whole midfoot unlocks and flattens. This produces a few extra degrees of apparent forward travel by collapsing through the middle of the foot, rather than rotating over the top of it. The leg gets what it asked for. But pronation of the foot is mechanically coupled to internal rotation of the tibia. Roll the foot in, and the shin bone above it spins inward with it. That coupling is anatomical and unavoidable, and it now creates a problem one joint higher, because the femur above does not spin inward by the same amount. 2 bones rotating at different rates, meeting at a joint. The knee is where that mismatch gets absorbed. The tibia turns underneath a relatively stationary femur, and the kneecap, which is anchored to the tibia below by its tendon and pulled from above by the quadriceps, is dragged off its centered path in the groove. The second borrowing route is the knee itself, moving sideways. Watch someone with a stiff ankle squat down. The knee does not track forward over the second toe. It slides inward, toward the midline, sometimes far enough that the two knees nearly touch while the feet stay apart. That inward collapse is called dynamic valgus, and it is a range-finding strategy. A knee that cannot travel forward can still travel diagonally, and diagonal travel buys depth. What it costs is the angle of pull on the kneecap. The quadriceps does not pull straight up the leg. It pulls up and slightly outward, because the hip sits wider than the knee. That outward pull is normally balanced by the depth of the groove the patella sits in, and by the vastus medialis holding it from the inside. Let the knee drift inward, and that outward pull angle increases. The kneecap is pressed harder against the outer wall of its groove, and the load that was designed to spread across the whole undersurface concentrates onto the outer facet. Repeat that for a decade of stairs, and the outer facet is doing work the whole surface was built to share. The third route is the hip and the trunk. Some people avoid both of the above by simply bending further forward at the waist. Lean the torso, and your center of mass moves ahead of your feet without needing the shin to travel at all. It works. It is also why the quadriceps ends up doing less and the lower back doing more, and why the knee ends up passing through a smaller flexion range, which sounds protective and is not, because a knee moving through less range spends more time loading the same narrow band of cartilage. There is a clean experiment that shows all of this happening on command. Macram and colleagues published it in the Journal of Sport Rehabilitation in 2012. They took healthy people with no knee problems, had them squat normally while measuring joint angles and muscle activity, then put a wedge under their heels to artificially restrict ankle dorsiflexion, and had them squat again. Same person, same session, same knees. The only variable changed was how far the ankle could travel. Knee flexion decreased, knee valgus increased, quadriceps activation dropped, and soleus activation rose. The movement pattern that gets associated with knee pain appeared within minutes of restricting an ankle, in people whose knees were completely healthy that morning. That is not a correlation between two things that happen to occur together in the same population. That is an ankle restriction being applied and a knee mechanics change coming out the other side. Fong and colleagues found the matching relationship in landing, published in the Journal of Athletic Training in 2011. Greater available ankle dorsiflexion was associated with greater knee flexion on landing and lower peak ground reaction force. The ankle that bends absorbs. The ankle that does not transmits. And Dill and colleagues, in the same journal in 2014, compared people with and without patellofemoral pain and found the painful group had less weight-bearing dorsiflexion. Notably, the difference showed up on the weight-bearing measurement, the one where the foot is planted and the body is on top of it, rather than on the version done lying down with someone pushing your foot, which is exactly what you would expect if the variable that matters is range under load rather than tissue length at rest. None of that proves that every stiff ankle will produce a painful knee. Plenty of other things load that joint. But the direction of the effect is consistent across the measurement work, the pain population work, and the experimental work where the restriction was applied deliberately. Here is the anatomical fact that explains the whole timeline. Articular cartilage has no nerve supply, none. There are no nociceptors in it, no free nerve endings, nothing that can generate a pain signal. You can wear the surface of your kneecap down considerably and feel absolutely nothing, because the tissue being worn is incapable of reporting its own condition. This is why knee osteoarthritis is so often described as arriving suddenly. It does not arrive suddenly. It arrives silently and then becomes audible, and the moment of becoming audible has nothing to do with when the process started. What eventually generates the pain is everything around the cartilage. The bone underneath it, the subchondral plate, is densely innervated. As the cartilage above thins, load transmits more directly into that bone, and the bone responds by remodeling, thickening, and in some cases developing marrow lesions that correlate strongly with reported pain. The synovial lining of the joint becomes irritated by cartilage debris and inflames, and synovium is richly supplied with nerve endings. The infrapatellar fat pad, sitting just behind the patellar tendon, is one of the most heavily innervated structures in the entire knee, and it gets compressed and irritated when tracking changes. The lateral retinaculum, the fibrous tissue on the outer side of the kneecap, tightens under sustained lateral pull and becomes a pain source in its own right. Every one of those structures reports late. They report after the mechanical problem has been running long enough to change the tissue around it. And they report in a pattern worth recognizing, because the pattern points straight back at the mechanism. The pain shows up at the front of the knee, around or behind the kneecap, rather than at a spot you can put a fingertip on. It is worse coming downstairs than going up, which is the load arithmetic from the last chapter arriving as a symptom. It appears after long periods sitting with the knee bent, in a cinema or a car or at a desk, and eases when the leg straightens out. Clinicians have called that last one the theater sign for decades. Nobody describes it as an ankle problem. It presents entirely as a knee problem, at the knee, years after the ankle stopped giving the knee the room it needed. So there is a gap, a long one. On one side of the gap is a measurable mechanical fault that produces no symptom. On the other side is a symptom that appears once the fault has done enough work. The gap between them is measured in years, and for most people it is measured in decades. The wall test sits on the near side of that gap. The strongest evidence that it genuinely predicts, rather than merely accompanies, comes from a study by Bachman and Danielson, published in the American Journal of Sports Medicine in 2011. They measured ankle dorsiflexion range in junior elite basketball players, healthy at the time of measurement, and then followed them for a year to see who developed patellar tendinopathy. Players whose ankles measured at or below a threshold of 36.5 degrees went on to develop the condition at roughly twice the rate of those above it. The measurement was taken while the knees were fine. The prediction was made before the symptom existed. That is the design that separates a predictive test from a descriptive one, and it is the design that most musculoskeletal screening never bothers to run. Be honest about the limits of it. That study looked at young elite athletes, not 60-year-olds on stairs, and at patellar tendinopathy specifically, rather than the whole spectrum of knee pain. The population is narrow, and the follow-up was a single year. It is one study, but it points the same direction as the experimental work, the pain population work, and the basic mechanics, and when four independent lines converge on the same explanation, you are usually looking at something real. The practical consequence is worth sitting with. A person who measures 7 centimeters today with no knee pain at all is not a person whose knees are fine. They are a person whose knees are still quiet. Those are different states, and only one of them is visible from the inside. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. Nobody wakes up one morning with a stiff ankle. It closes by fractions of a degree over decades, and 4 things close it. The first is tissue chemistry. Collagen molecules in tendon and joint capsule accumulate cross-links with age, chemical bridges that form between adjacent fibers and progressively reduce how far the tissue can glide and lengthen. The Achilles is one of the largest tendons in the body and one of the most affected. The posterior capsule of the ankle joint stiffens alongside it. This process is real, it is age-related, and it is the part you cannot fully undo. The second is the muscle almost nobody targets. There are 2 calf muscles that matter here, and they behave completely differently. The gastrocnemius is the visible one, the diamond-shaped bulge, and it crosses 2 joints. It starts above the knee on the femur and ends at the heel. The soleus sits underneath it, flat and broad, and crosses 1 joint only. It starts below the knee, on the tibia and fibula, and ends at the same heel. That difference decides everything about which one limits you and when. Bend your knee, and the gastrocnemius goes slack. Its upper attachment moves closer to its lower one, and it stops being able to restrict the ankle at all. The only muscle still holding the ankle back is the soleus. Now consider the positions where dorsiflexion actually matters. Squatting, knee bent. Descending a stair, knee bent. Standing up from a chair, knee bent. The wall test you did at the start of this video, knee bent. deliberately, because that is the point. Weight-bearing dorsiflexion in a bent knee position is a soleus limited motion, almost every time. And the standard calf stretch that everyone has been shown, the one where you lean against a wall with the back leg straight and the heel down, targets the gastrocnemius. Straight knee, gastrocnemius tight, gastrocnemius stretched. It is a perfectly good stretch for a muscle that is not the one restricting you. People stretch faithfully for years and their wall test number does not move, and they conclude their ankles are just stiff, their ankles are fine. The stretching was aimed one muscle too high. The third factor is what you wear. Almost every shoe made has a heel higher than its forefoot. The gap between them is called heel-to-toe drop, and a typical running shoe runs 8 to 12 millimeters. A work boot or a dress shoe can run 20 to 30. A raised heel means the ankle starts every step already partly plantarflexed, which is to say already partway through the range in the wrong direction. Every millimeter of drop is a millimeter of dorsiflexion the ankle never has to produce. Tissue adapts to the range it is asked to visit. Reduce the demand for 30 years, and the supply follows. The fourth is the ground itself. Modern surfaces are flat, level, and predictable. Pavement, floorboards, tile, tarmac, uneven ground drives the ankle through varied ranges constantly. Hundreds of small, unrepeated excursions per walk, and almost nobody spends time on it anymore. Put those four together, and you get something that gets called aging, but is mostly disused wearing aging's clothes. The cross-linking is genuinely age-driven. The rest is a range that stopped being visited. That distinction matters enormously, because the parts driven by disuse respond to use, and they respond faster than most people expect. Start with why the obvious approach underperforms. Passive stretching lengthens tissue under no load. You hold a position, the tissue creeps a little, you stand up and walk away. What the knee needs is range available under body weight, in a bent knee position, produced fast enough to be useful during the 400 millisecond window of a step. Those are different capacities, and training the first does not reliably deliver the second. The drill that does deliver it is the test. Take the position you started this video in. Foot flat, heel pinned to the floor, knee driving toward the wall. Rather than measuring once, rock in and out of it. Drive the knee forward until you feel the block at the back of the ankle. Hold for 2 seconds, come back. 20 to 30 repetitions per side, once or twice a day. Keep the heel down. The instant the heel lifts, the repetition stopped counting. Progress it by moving the foot back a centimeter once 30 repetitions feel easy at the current distance. That is a loaded end-range stimulus applied to the exact position and the exact joint angle that matters, which is why it moves the number when passive stretching does not. Second drill, and this is the one that reaches the soleus. Stand on a step with the balls of your feet on the edge and your heels hanging off. Bend your knees slightly, 10 or 15 degrees, and keep them bent. Now lower your heels slowly below the level of the step. Take 4 seconds on the way down. Pause at the bottom. Come back up. 10 to 15 repetitions, 2 or 3 sets. The bent knee is not optional. Straighten it, and you have converted the exercise back into a gastrocnemius drill, and you will feel the difference immediately in where the stretch registers, several inches lower and deeper than the usual calf stretch. Third, spend time in a deep squat with the heels down. Feet flat, hips low, hold for 30 to 60 seconds. Hold a door frame or a counter for balance if you need to, and if the heels will not stay down, put a book under them and use a thinner book each week. This position loads dorsiflexion at end range under body weight for a sustained period, and it also opens the hip and ankle together, which is closer to how the joints actually cooperate. Fourth, walk on your heels. Lift the forefoot completely off the ground, toes toward the ceiling, and walk 15 steps forward. This trains the tibialis anterior, the muscle on the front of the shin that pulls the foot upward, and that muscle is loaded during normal walking at only 10 to 15% of its capacity, which is nowhere near enough to maintain it. Heel walking also relaxes the calf through reciprocal inhibition. When the front of the shin contracts hard, the spinal cord automatically dampens the motor neurons feeding the calf behind it. You get a strengthening stimulus in front and a release behind from the same 30 seconds of work. Fifth, and this one runs in the background, reduce the heel height you stand in. Not overnight, because the Achilles has adapted to the height it has been given, and dropping 30 millimeters in a week is how people end up with tendon pain. Move down in stages over months. Spend more time barefoot at home and on uneven ground when you can find it. Put together, a day looks like this. 30 seconds of heel walking to wake the front of the shin. 20 knee-to-wall rocks on each side. 2 sets of 12 bent knee heel drops off a step. 1 minute in the deep squat at the end. Somewhere between 8 and 10 minutes, and none of it needs equipment beyond a step and a wall you already own. Do it most days rather than all days. The tissue adapts to a repeated stimulus, not to a heroic one, and the people who go hard for 9 days and stop have achieved less than the people who did half as much for 6 weeks. Timelines. Range under load usually starts to move within 2 to 4 weeks of daily work, and the early gains come mostly from neural tolerance rather than tissue change. The tissue follows more slowly, over months. Retest with the wall and the ruler every 2 weeks, and write the number down each time, because the change is gradual enough that you will not feel it, and precise enough that a ruler will catch it. Some cautions, and they are not decorative. If you have current knee pain, an ankle injury, an ankle replacement or fusion, reduced sensation in your feet, or a balance problem, work near a counter you can grab and get the knee assessed properly, rather than assuming the ankle explains it. A hard block at the front of the ankle joint that stops abruptly and feels like bone rather than stretch is a different problem from a soft tissue restriction, and it needs looking at rather than loading. And keep this in proportion. Ankle dorsiflexion is one contributor to knee load among several. Hip abductor strength decides how much the femur rotates and drops. Quadriceps capacity decides how much force gets absorbed before it reaches the joint. Body mass multiplies everything. Prior injury changes the whole picture. The ankle is the one that gets missed most consistently, which is why it is worth a video, but it is not the only thing loading that joint. Go back to the gap between your 2 legs. If one ankle gives 11 centimeters and the other gives 7, you are not looking at a person with a stiff ankle. You are looking at a person with 2 legs, solving the same problem in 2 different ways, thousands of times a day, and only one of them is borrowing. That asymmetry is more informative than either number by itself, and for a specific reason, it removes the population question. Comparing your figure to a published average means arguing about whether the average applies to your height, your build, your history. Comparing your left leg to your right leg removes every one of those variables. Same body, same weight, same shoes, same stairs. Any difference between them is the leg, not the person. A gap of more than about 2 centimeters means one side has been compensating and the other has not, and it is worth knowing which knee that is before it tells you itself. There is a wider principle underneath all of this, and it is the reason a range of motion measurement can predict anything at all. Joints keep the range they are asked to use under load, not the range they are stretched into occasionally, the range they are required to produce, repeatedly, while carrying weight. A range that stops being demanded stops being maintained, and the tissue reorganizes around the smaller territory it has been given, and none of that produces a symptom because there is no receptor anywhere in the body that fires when a range quietly narrows. The knee is the joint that pays for this more than any other, because of where it sits. It is a hinge caught between 2 segments that both rotate. The hip above it rotates in 3 planes. The foot below it rotates and pronates and supinates. The knee, structurally, bends and straightens and has only a few degrees of rotation to give. When the joints on either side of it stop doing their share, the knee is the one holding the mismatch, and it holds it under 3 times body weight on every stair. That is why an ankle measurement predicts a knee outcome. The knee is downstream of the ankle in the most literal mechanical sense, and it inherits whatever the ankle refuses to do. So go back to the wall. You have 2 numbers written down. If they are both over 10 and within a centimeter of each other, your ankles are giving your knees the room they need. And the job is maintenance. Keep visiting the range. Do not let the years take it back quietly. If either number is under 9, or the two are more than 2 centimeters apart, you have found something that is currently costing you nothing and will not always be free. 20 rocks at the wall, a set of bent knee heel drops, a minute in a deep squat, 10 minutes, most days. Retest in a fortnight with the same ruler and the same wall. My grandmother watched people come down the stairs and she knew, months ahead, who was in trouble. She was not measuring anything. She was reading the last visible sign of a range that had been closing for 20 years, and by the time it showed in someone's gate, it had been available to a ruler for 2 decades. You have the ruler. Use it before the stairs tell you. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.